Before kind of digging into what we did, I think especially kind of coming from industry, it's sometimes helpful to motivate sort of like the actual real world problem that we're solving. So I'll tell you a little bit about like what we use machine learning for at Stripe, at least a subset to start and to kind of like motivate how we approach these problems. So if you're not familiar with Stripe, we basically provide a toolkit for starting and running an internet business. If you want to run a business, you usually want to be able to like make money. So a core piece of that was sort of the founding piece of Stripe is online payments and rich APIs for that. And then we've built kind of other complementary layers and additions to help with things like incorporation or fraud or with platforms. One thing that's interesting about our use of machine learning is that it is the case that our users are businesses doing pretty critical stuff. So, you know, in some cases of machine learning, maybe you're like suggesting a recommendation, and if somebody doesn't like it, well, they'll click on something else. But in our case, we're kind of like operating on, you know, many, many businesses that live in the real world and have real customers. And so we need to make a lot of decisions quickly, but also accurately. Like sort of the worst case of machine learning for us would be that we, you know, accidentally shut down someone's business or block all of their transactions. So that frames a lot of our thinking about how we want to do things for production in ways that are reliable and reproducible. And so a couple of the ways that we're using machine learning in our user-facing products, the most prominent usage is in Radar, our fraud product, which is shown here, where basically every time you know, you like order Postmates or do something with a Stripe user, kind of in that charge flow, we're evaluating what is the likelihood that that charge is fraudulent and blocking it potentially if we think that it's likely, and also kind of giving users some tools to kind of help manage that or write extra rules. Another example of machine learning for us is in our billing product, which is for, you know, businesses that operate with subscriptions. And so we use machine learning to help us do smart retries when a subscription charge fails to kind of figure out when or how to retry it so that it, you know, it may go through for the business. And these are just kind of a couple of uses of machine learning in our user-facing products. We also use machine learning in quite a few places internally for things like different types of risk management or for things like suggesting resolutions for customer support and things like that. And so now I'll tell you a little bit about like how do we do model training for these types of applications and focus in a little bit on Radar, our fraud product, as the example there. So this is sort of you know, a very simplified view of what could be a training data set for evaluating fraud. So each of the left 3 columns are potential features. Each row is like an observation, and then the rightmost column is the label. So these are things like, you know, how much was the transaction for, what country was the card issued in, more complex kind of like counter type features of, you know, how many countries was this card used from in the past 24 hours. If you have some credit card that's been used from like 7 countries in the past 24 hours, that's a little bit suspicious. So this is kind of like, you know, the type of data, although a lot more of it and more complex than this, that we might be using to train a model. And then, you know, basically what we want to do, like any machine learning problem, is turn it into a matrix and like fit some function to it. On the right, there's a decision tree, but it could be whatever you want it to be. And then, you know, try and have something that will generalize to whatever inputs, to use the first and -1 columns to predict the label column. And then in the Radar case, we are basically, you know, trying to have really good outcomes for our users. And, you know, if, for example, we have a false positive, then we may block a legitimate charge, or if we have a false negative, we may let a bad charge go through, and those are pretty bad outcomes. And then we always want to measure our models as we do any training process, just the way you would for anything, maybe with some kind of precision recall curve or ROC or AUC. And then we'll set the thresholds that we use if we're doing something like blocking. Okay, so basically in kind of our early days of working on these types of problems, we did training pretty manually. Like a data scientist or a machine learning engineer would maybe write some kind of MapReduce or Spark job or write a SQL query. They'd generate some Parquet data, and then they'd like, you know, import scikit-learn or import XGBoost in a notebook and like put together all of their data, transformers, encoders, serialize the model, and manually deploy it to production. And basically, as we started to, have sort of more serious usage of ML in our production systems, and in particular really want to automate things, we kind of took a step back to decide, like, really how should we be doing model training? So these are kind of the requirements we came up with. We wanted it to be easy to get started. We didn't want to take that away from people, because often, there's sort of this question of, like, can I make a model good enough that it's useful to use in this product? And we don't want to make that harder. One thing that was really important was we wanted to be flexible. There's like a Cambrian explosion of different libraries, frameworks you can use for machine learning, and we use a number of them at Stripe. Like, in addition to more traditional things like scikit-learn and XGBoost, we use like PyTorch, FastText, Prophet, and we wanted to make sure we could support those. We want everything to be automatable. If we're going to train like hundreds or thousands of models every day, you don't want someone to have to sit around and kind of like kick all that off and manage it. As we've grown more use of ML, we realized the importance of tracking and reporting, both things like kind of the data lineage, as well as just like, which team is it? What are they doing? When did they do it? Did they get an error? And then more like on the infrastructure side, we increasingly wanted to make sure that everything was reliable, secure, and then kind of taking away the burdens of resource management from people developing models at Stripe. Like, people don't really want to think about what instance type this thing is running on, or kind of the details of what they need. They kind of just want stuff to work as much as possible. And so basically, the way we approached this was to kind of break this into two chunks that I'll tell you about. One that manages more of like sort of the usability requirements, which we built an API for, which we call Railyard. And then the other that manages a little bit more of sort of our infrastructure side, which was basically kind of getting this to run on Kubernetes. And so, when we were thinking about how can we make model training better and have it be usable, reliable, reproducible, early on, we'd kind of like taken people's training code and put some CLI tools around it and made it just like a little bit easier to do common things like fetch features, train models, evaluate results. But that still wasn't kind of going to scale to this hundreds or thousands of models a day that we wanted to do. So we kind of looked to Stripe itself for inspiration, because Stripe is kind of like an API company where we make it really easy for users to automate things like payments. So this is an example of the Stripe API docs, which is something that I think people really appreciate about our product. And we tried to kind of like learn from what Stripe does well. And so what we ended up with is basically, in thinking about the design, kind of breaking things into two pieces to kind of give us this ability to automate, but also have a lot of flexibility for users. So we thought about, like, should we have a DSL for encoding components in specific frameworks? But that's kind of like, it's hard to get everything in there. You're constantly going to be behind. You're not going to be able to keep up with all the latest frameworks. But we did want people to be able to kind of like easily automate, which I'll tell you more about as well. So we ended up with these kind of like a couple of components where the model training workflow is kind of like freeform Python code, where I'll tell you more, but you just kind of have to implement a train function. And then the part of your request that you want to automate is basically the API request itself, and then that will reference the workflow. And then Railyard itself is a Scala service, so it has JSON endpoints for training models, for fetching the results of model runs. It kicks off the training job and does the job state management. And basically, like, you send it a post request, and then you get back a job ID that you can then get more information about. So here's an example of what a workflow looks like. And the workflow is kind of like the contract between Railyard and your model, where we give the workflow some label and feature data endpoints, and the workflow returns back the trained model as well as the data sets that you used. And the workflow inherits from a parent workflow class, and then it just has this one method here, train, that you absolutely have to implement. And so this is sort of an example of a minimum Python workflow for XGBoost, and you can see kind of some of the different parameters, and then it returns back the fitted pipeline. The other piece is the API request itself, which has a few different components: metadata, data, filters, holdout data, and training. So the request starts with the metadata that's shown here, which is really important for us for tracking provenance of who is training and what they're doing, and doing things like splitting out success and failure metrics by team or by perhaps individual. And this helps us do things like profile long-running jobs or provide feedback. I should mention too, I guess this API is, all the examples I'll show you are using JSON, but we also designed with proto support in mind for in the future when we migrate to gRPC for Railyard. The next section here is like where you specify your data. The most important thing is kind of like the path for your features and where they come from, which in this case is Parquet, that in most cases for us is something that's generated by our features framework, which is a different but interesting talk. When people are experimenting, we also give them an ability to specify this as like a SQL query that can be run on our data warehouse. But that's kind of more for experimentation and it doesn't work as well for reproducible production cases. And then in the case that you're going to be like splitting out your data set by date, there's also the date column shown here. The next component is this filters section, and this is sort of built around Parquet in particular, where we want to support predicate pushdown. And then we support basic comparison and equality operators, some support for set membership. And if you want to do something more complicated, you can put it into the workflow. The next chunk is the holdout data. So this is just like, how are you separating your training and test set? This example is what the API looks like if you're doing that by date, but you can also do things like random or stratified sample. In the case where you have by date, then there's also some parameters to kind of specify what the date column is and the start and end date. And then maybe most importantly, the last chunk of the API is the train section for the API request, where you're going to specify what is your workflow, what are the feature names, and that's in case you kind of want to rewrite what those are inside your workflow. What is the label column? And then maybe one of the most important pieces is this custom params, where just depending on what your model type is, people are going to want to do different things and automate on different things. And this has kind of been like invaluable to us. And there's not a lot of requirements. It just has to be like a map string JSON. So it just has to be some kind of key value pairs. And the most common use case we've seen for this is hyperparameter optimization, which is probably something we're going to build first-class support into in the API in the future. But this really varies a lot and has been like a core part of what's allowed us to support all these different model types and frameworks. Oops. And so if you're the user, this is sort of like what your interaction looks like, where you post to the train endpoint with your request. What you get back is this job ID. And then you can check the status of the request, or you can fetch the result. And you can also automate these into other services. And then when we're looking at the result, here's an example of a successful job that's been run. So some of the things you can see are like, what is the path for the logs, which is pretty important. When did the job complete? What was the git SHA, so that we have an idea of what code was run. Where are the data for your holdout data and labels, which we then usually send on to kind of our evaluation service, but users may also do other things with them. And then diorama ID is basically, diorama is our model prediction service, so this is the ID for the serialized model, which is the thing you can just directly serve in production. So we're kind of taking care of that serialization and persistence step in here as well. And then there's an exception info field, which here is null because this completed successfully, but if your job failed for some reason, this will give you a lot of information about why and maybe a link to like the full error traceback or something like a sentry page. Let's see. Yeah, and then one of the key pieces for us, especially for things like Radar, where we want to train like many models on a regular cadence, is that these basic components give us the ability to then add additional things into the system to automate. So one of the things we have is a retraining service where you can specify, how often you want to retrain and which model sets you want to retrain. For folks who train models in more of kind of like a DAG-based workflow setting, we've also had people like automate Airflow tasks that call out to Railyard as well. So a lot of different ways that people can kind of build on these components we've given them. And then just stepping back, I've kind of told you about what are the components we use on the training data side, but these do also kind of fit together with a bigger system. So as I mentioned, at the end of your workflow, you get like a model ID that corresponds to a model package, which is how your serialized model is persisted. And then also at the end of your model evaluation for each application, like for Radar, we have a tag. And then the output of that will be sort of updating the tag, the model that you want to serve for that tag, which then we can score with Diorama, our real-time inference service. So everything kind of like fits together nicely for users. So just kind of from this part about how we design the API and workflow, some of the lessons we learned are on the API being really flexible with what parameters we let people input. And we found that not using a DSL was the right choice for us, and that would have been too restrictive. And also that tracking model provenance is really important, especially when we have more users. Like we used to have people kind of pop into the team Slack channel and say, it's kind of like, my job failed, can you help me? And then you spend a long time tracking down, like, what code did you run, where did you run it? And now kind of if we have the job ID, we can figure out everything else by ourselves, or even kind of like proactively reach out, which has been a big improvement. And then on the workflow side, just kind of getting the interfaces right, I think, was something that took a little bit of work for us. People will load and transform their data in ways we don't anticipate, but having these standard API interfaces like fetch data, preprocess, train, write evaluation data helps kind of dictate some of the serialized data containers that people will use while still being flexible about how they're generated. And then, like I mentioned, kind of baking into this model serialization and persistence was pretty helpful since ML engineers or data scientists like really don't want to think about that. They just want to get out a model that can be served. And then similarly to tracking model and provenance and ownership, just like measuring each step helps us understand and debug and tell, why is training a model taking so long, which is something that inevitably comes up a lot. Okay, so with that in hand, I'll talk a little bit more about more of the infrastructure side, where once we sort of had a way for people to more easily specify what they wanted to train it, we initially ran that just kind of on individual machines, and then eventually we realized we needed to abstract away a lot of the complexity of that and also make it just kind of like more reliable, reproducible, and scalable. And so we set up all of this to run on Kubernetes. So before we had this, basically the situation was like a little bit dire for people. We had some number of something like AWS instances that had different properties, like maybe they had a lot of memory, maybe they had GPUs. And people would kind of like choose which one to run their training job on. Sometimes maybe they'd get their own box, sometimes maybe they'd have to share. They didn't really know what else was running on them. And it was kind of hard to tell, will my job actually work on this? Like, I'm gonna have to check in and see what someone else is doing. There was kind of like a lot of coordination and a lot of problems. And this was true even after we had kind of like a training API in Railyard, where we were running this initially as kind of like a sidecar service, where we would parse the request and like execute the Python process on the box directly. Yeah, so this was a little bit unfortunate. Oops. And so by moving to Kubernetes and using that as the execution engine, it makes it a lot less likely that something will run out of memory, disk space, CPU, because we can use Kubernetes to help us with the resource allocation. So then our services is managing the job state and the API endpoints, but then it makes an API request to Kubernetes instead of managing its own Python process, which is a big improvement. And this is kind of how it works. One of the key things for us was figuring out like how we would get the Python code, including all the dependencies that we needed to run over to Kubernetes. And what we did was we ended up using the subpar library developed by Google. For a while, Stripe has been moving most of our builds to the Bazel build system because of its speed, correctness, reproducibility, and then its flexibility to work in a multi-language environment. And Bazel works really well kind of out of the box with subpar. So this was a good choice for us to help us bundle all of our Python requirements and source code into a single par file. And basically with subpar, you define the entry point to your Python executable, and then Bazel builds the par file that can be bundled into a Docker file. And then with that, you can also package up like any third-party dependencies you need, like if you need the CUDA runtime for GPU support for your PyTorch model, say. And then after the Docker image is built, we deploy it to, for AWS, the Elastic Container Repository to make it available for Kubernetes to run. And so basically, if you are a user developing models, your workflow is you kind of like, iterate with your workflow and on your branch during the testing and experimentation phase. And then, when you merge to master, a new Docker image is built as part of the build. And then you can deploy that almost like deploying code. And then now your job is kind of ready to be run on our Kubernetes cluster. And one of the nice things for us is that we have an orchestration team that runs kind of all of our Kubernetes clusters. And so that meant even kind of as a data infrastructure team, it took away like a large amount of the burden of sort of managing the underlying servers and infrastructure. And we got instead to operate at a higher level of abstraction, just like interacting directly with the Kubernetes API. This is kind of a picture of what it looks like. So clients interact with the Railyard API, which internally stores some state in Postgres. And then the Scala service interacts with the Kubernetes API. And then we can start training jobs on different resources very easily. And then from Kubernetes, we kind of pull back the logs, the serialized models, and the evaluation data. And one of the things you'll notice here is that there's also different types of workers, like CPU workers, GPU workers, high memory workers. So I'll tell you a little bit more about that as well. So basically, what we did was we added into our API like a sort of top-level resource for compute resource, which makes it, for resource types that we've made available, kind of like a one-line change to get one of these different types of resources that we've described. And so if you're a user, you can just think about CPU or GPU. You don't have to think about like p3.2x large or i3.16x large, which are really hard to keep in your head, even if you know a little bit about what instance types are like. And then basically internally, we kind of figure out for each of these resource types, like how to set the Kubernetes, what are called toleration and affinity, to help schedule the jobs on the cluster that kind of say, like, I would like to run my job on this type of node or affinity, but don't run other jobs on my node, which is kind of the toleration, which works a little bit like node tainting. And then we also, as part of each instance type, define a memory limit and a memory request. So there still is a little bit of trial and error because we're not very restrictive with what people can do in their jobs to make sure that they're going to fall within the limits. But it's a lot easier to kind of have all of that managed within Kubernetes and to know that, at some point jobs will get killed appropriately and that things will be managed in general a lot more consistently. This also makes it a lot easier for us to change the instance types that maybe correspond to different resource types, or to just like expand the set of like servers that we have in the cluster. That's a single command instead of what used to be a lot more work. All right, so that kind of completes the second chunk of like taking away the resource management piece and making everything reliable and secure. And what we learned here is the instance flexibility is really important because different machine learning workloads have really different needs. Like we may run in one day thousands of time series forecasts, or a long-running word embedding model, or a fraud model that's using hundreds of gigabytes of data. And just being able to iterate and scale all of that really quickly has been really important for us. As I mentioned, there is a little bit of trial and error in figuring out how to set up things like the the memory limits, and maybe like reschedule failed jobs, and that's something that we're still looking at. Using subpar worked really well for us because it integrates so well with Bazel. And then just kind of finding this right layer of abstraction for us as a data infrastructure team, where we no longer have to kind of think at the cluster or server level because we have a set of folks who are managing Kubernetes and kind of provide the Kubernetes API to us as a service, has made us a lot more efficient as an infrastructure team. And then I think it's always cool to see like how things actually work. So I just want to kind of show you some metrics from different dashboards of like what would a user look at, or like what metrics do we track as an infrastructure team. So this is an example of the dashboard from our model retraining service. So if you're a user and you know that like all of your fraud models are about to kick off for the day, you can kind of check on the status here. And you can see some of them have shipped, which means the model was trained and then the subsequent evaluation decided that it was better than the current model. Some of them, maybe failed, like in this case, maybe there weren't enough examples of one particular label in that training set. Some of them are still running, some of them are not shipped, where there is a new model, but it's not better than the old one, so we're not going to put it out. We also train what we call explanation models that are sort of like simpler models that are a little more interpretable. So you can sort of see what this looks like if you're a user. We can track operational metrics. So these are things like, how many or what is the rate of successful Kubernetes job creations, or how long is it taking to create a Kubernetes job? And these are things we can also alert on as an infrastructure team. So if we expect there to always be some jobs getting started and there's a long period where there aren't, we can alert and look into it without people kind of having to file bug reports and ask why training is broken. Some of our users have put together pretty complex workflows that do things like simulations also, and so we can break those out and track timing and errors as well, which tells them a lot about like where things might be going wrong or where they might want to invest their effort. And then just in terms of sort of the scale or numbers, we have like a number, probably dozens of workflows that are set up using Railyard for things ranging from user-facing products like Radar to payment optimization, to more internal-facing applications like risk management or customer support. Some of the libraries we use are shown here, things like scikit-learn, PyTorch, FastText, XGBoost, and Prophet. Every week we train in total we've trained hundreds of thousands of models, and we're training thousands more every week. We use different resource memory types with GPU, CPU, and high memory. And then in the end, if you think back to kind of like the full system picture I showed, all of these models that in the end come out are used to make hundreds of millions of real-time predictions every day. And this, I think, is like sort of an interesting slide to show the impact of kind of all of this on the end users, our ML developers at Stripe, where for a long time, we did not train very many models per week because people were just kind of doing it by hand. And it was a lot of work. And then as we gave people an API and people started automating things, we started seeing these spikes where suddenly there were a lot more models trained. But it's kind of buggy and maybe driven by mostly one or two applications. And then as we kind of got rid of people having to worry about the resource management and like which box their thing was running on or what instance type it needed, that's really helped us just kind of scale up and have things go up and to the right in terms of like the development that people are doing and how that's going. So here's sort of a summary of all the things I've talked about. We built a simple but flexible API for running and automating training workflows. We do our resource management in Kubernetes. We really try to instrument everything along the way to help us debug and profile. And then basically, these are the systems we use to train thousands of models per week for this range of different applications. We have periodically run like quarterly surveys of ML developers at Stripe, which are really interesting user feedback. So around the time that we sort of shipped this, these are a few of the comments we got. So things like, Railyard has made it much simpler to write a new pipeline. When my new teammate started, I could just point them toward docs to get him going. And people on my team were relieved to hear that the training code used a standard way of doing things, so they didn't have to just ask others how to do it. Or this saved me time by abstracting away the tedious parts of training and letting me focus more on building features and model architecture. So thanks for listening, and happy to answer questions. I particularly want to thank some of the folks on our machine learning infrastructure team who worked on this. And if you or anyone you know is interested in interesting data roles in here or in Seattle or for remotes, using data to build ML products and track and move money, I'd be happy to talk to you about that as well.
How do you deal with the features which are used in all these pipelines? Like there would be like tons of features. How do users get those features?
Yeah,
as well as
so that's an excellent question, which is a talk into itself. One of the things we've spent a lot of time working on the past year or two is having like sort of the right abstraction for people to define features where they only have to write code once, and it can be available for training, for batch jobs, and for online jobs. And so that you can potentially, if it makes sense, like share features between applications. And so we've done a lot of work to kind of build a DSL for that has different compilers or backends that can run like on Spark for maybe your training, or on kind of like a Kafka consumer setup for real time, but where the feature code is the same. And that does allow a lot of what you said, where you can almost like sort of browse the features and be able to use the same features in different models, which has been really powerful for us, especially since we often have, like, even in the case of risk management, there's a lot of sort of related applications where you might want similar features and inputs.
A few slides back, you kind of had your dashboard where you showed failed, shipped, et cetera. And you mentioned, the iterative process where you're kind of comparing results of models, and then if it was better than the other ones, then it would ship. So I'm wondering, maybe you don't always want, if it's something's better than the previous model, you might not always want to ship it to production because it's still something you're kind of evaluating. So how do you control that?
That's a really good question. And it's also something that's like a little bit different for each application. And we're trying now to kind of capture that more flexibly in sort of like an evaluation API, where you tell us like what are the metrics you care about and how they connect. So in the case of some of our applications, people do things like they want to say something like maximize the recall at a fixed false discovery or false positive rate. And if you meet that for any given model, which it might be some kind of global model, it might be segmented for a user or particular users, then that's like ship it, right? And then the second part of what you said, maybe there's a little bit of definition around like what does ship it mean? Like, are you going straight out to production, or how do you manage that rollout? So that's something right now that mostly applications manage themselves, where like usually they'll kind of push the updated model to almost like a candidate tag, and then do some kind of like feature flag or A/B testing, or maybe in the future, and for some applications, some kind of bandit. But that's something that eventually we kind of like hope to offer a little bit more standardized functionality as well.
How do you solve the problem of one job kind of cannibalizing all the resource, CPU, RAM, causing, especially if it's over a weekend, it's causing delays for other jobs?
Yeah, so that's a lot better with Kubernetes, because you can do things like set the parameters they give you for this, are things like this toleration and affinity of sort of like, I want this job to run on these nodes and don't run other jobs there. So it's not exactly one-to-one, but it gives you like a lot more control and isolation for your particular job. Like I mentioned, we do also have, we set hard and soft limits, and sometimes people go over those because we let them do like basically arbitrary things. So there is a little bit of tuning around that, but overall, I think the rate of like something being killed because it's like using too much memory is like pretty low at this point. So it's something that we're able to work with a lot more easily than previously.
How do you guys handle dependencies? Let's say you have one of these embedding models that somebody retrained, and hundreds of other models depend on it. How does your API handle that? Yeah,
so that's an excellent question. And I guess that's mostly outside the API, but it's something that we deal a lot with. And so one thing that's maybe interesting in this slide, the StyROM ID, that's a SHA-256. So it's like sort of a hash of the bytes. And so we have kind of like this notion of immutable models. So anytime something is different, you're going to have to update that SHA. And that's one thing that keeps you from like stomping over something else. We also have kind of what we call like a concept of meta models, where you can sort of like compose different models. So you could have like model A either depends on model B, or maybe it shells out. So maybe you have a case where it's like, use this model if there's not a specific model for the user. If there is, then shell out to that. And all of that will be specified kind of like using these immutable SHAs. So basically, that kind of prevents us from getting in a situation where this thing changed underneath you and you didn't realize it. And then the thing that's mutable is just the tag to SHA mapping, where the tag is your application. So in the end, you say like, radar currently points to this SHA, and then that SHA may actually like shell out to some number of other SHAs as well.